Good evening to everyone and welcome to today's webinar. I'm Dr. P. Vijayan and I'm one of the organizers and also going to act as a moderator for this webinar on current and future trends in electrocatalysis for energy, fuel production and nanosensors development. I'm privileged to be hosting this webinar today. Before we move on to the welcome address, I would like to share few information about this webinar. First, today's webinar recordings will be available on YouTube. If you have any questions for our speakers, please post it in chat box. We will be answering questions at the end of the session. If you don't get to your question during today's webinar, we will be sure to follow up afterward. At the end of the session, feedback form will be shared in chat box. Please fill up your personal details carefully, as it is going to print on e-certificate. So without any further ado, I would like to hand the session over to Dr. G. Rajagopal, HOD, Department of Chemistry, Chikana Government Arts College, Tirupur. Over to you, sir.
Thank you, Vijayan. Good afternoon to everyone. I am here for welcoming all you people for this webinar. Good afternoon to everyone and welcoming you all for today's international webinar on current and future trends in electrocatalysis for energy, fuel production and nanosensors development. I feel privileged to be here and welcome everyone. Respected Principal Madam, today's resource people, Dr. Arunprakash Periyasamy and Dr. Surrey, my dear colleagues, teaching faculties, researchers and students from various institutions, warm greetings to one and all. On behalf of Chemistry Department of Chikana Government Arts College, I extend a warm welcome to our distinguished Principal Madam, Dr. C.V. Deepa. More than 30 years of her rich experience in academic and administrative side, Madam has enlightened our institution to an elite level. She is always informative and instructive. Welcome, Madam. Next, I extend my warm welcome to our young speakers, Dr. Arunprakash Periyasamy, Postdoctoral Research Associate from University of Surrey, UK, and Dr. Surrey from Senior Scientist from Sikri, Karaikudi. The common specialty of our guests are both are from our own family, that is both eminent speakers received their UG degree from Government Arts and Science Colleges in Tamil Nadu. Dr. Arun from Government Arts College, Udumalapet, and Dr. Suresh from Government Arts College, Salem. Naturally, you both are inspirational and motivational for our students. CSIR Sikri is a publicly funded organization and it excels in all aspects of electrochemical science and technology and to develop globally competitive and eco-friendly technologies in energy, environment, health, and materials conservation. Dr. Suresh has helped a lot for our MPhil scholars, allowing them to do collaborative research work at his lab and published a paper along with our faculty members, Dr. Vijayan and Dr. Sivadayanidhi in Bulletin of Material Science, an international journal with impact factor around 2. It's giving me a great pleasure to welcome both such magnificent researchers for this international webinar. Welcome, scientists. Regarding this topic, nanosensors with the high sensitivity utilize electrical, optical, and acoustic properties to improve the detection limits of analyze. The unique and exceptional properties of nanomaterials are exploited for sensing purposes. High sensitivity in analyte recognition is achieved by pre-processing of samples, signal amplification, and by applying different transduction approaches. The use of such nanosensor sensitivity and selectivity can offer different advantages in biomedical applications. Like earlier reduction disease, toxins are biological threats and create significant improvements in clinical as well as environmental and industrial outcomes. The field electrochemistry is having 300 years of a long history starting from Luigi Galvani to till date, Nernst, Bartel, Nobel laureate Heveroski. Electrochemical detection is so popular due to extraordinary characteristics including sensitivity, low cost, compatibility with modern miniature or lab-on-chip type strategies, least requirements of power, and requiring no pre-sample processing. Similarly, electrocatalysis deals with the catalysis of redox reaction and is a key discipline for the development of energy storage, fuel cells, solar cells, and all other electrochemical devices in which the control of interfacial charge transfer reactions plays an important role. like the Internet of Things, IoT, there is another terminology, IoNT, Internet of Nano Things. The interconnection of nanosensors and nano devices with the Internet has led to the development of concept based on IoT called Internet of Nano Things, IoNT. Okay. By seeing this importance, I hope today's topics are essentially needed and noteworthy. Thank you for selecting this topic, scientist. Next, I would like to welcome organizers of this webinar, Dr. K. Kaniyappan and Dr. P. Vijayan. It is not enough to welcome them with a single sentence. Dr. Kaniyappan, a sincere teacher who maintains our department library without any compromise for the past 4 years for the benefit of our students and faculty. He has taken much effort to train and support our team to learn a learning management system. Welcome, sir. Dr. Vijayan, who has done his postdoctoral research work at Taiwan, and a young and talented worker of our department in all aspects. He is technically coordinating all our virtual activities. Welcome, sir. My special welcome to Dr. N. Sampath Kumar, IQSC Department Coordinator, who has initiated and scheduled all these activities and the encyclopedia of our department. Welcome, sir. It gives me a tremendous contentment to welcome all my department colleagues by name. Dr. N. Sivakumar, who is an expert in absorption, Dr. S.P. Raja Singh. He is also a postdoctoral research fellow from world-famous institute, Weizmann Research Institute, Israel, and an American patent holder, expert in synthetic organic chemist, digitalizing all our department activities. Next, Dr. Karthikeyan and Dr. Sivadeyanidhi. They are known for nanotechnology and polymer composites fields, respectively. Welcome, sirs. Next, Dr. Sujata, an expert in coordination, Dr. Balamani, an expert in organic, Dr. Satya, an expert in organometallic chemistry. All the three are having rich experience in teaching pedagogy and used to give periodical counseling for our students and won applause in their respective field. Welcome, professors. With the foretaste of this, I welcome the participants from various institutions, senior professors, faculties, and researchers and students. Welcome you all. Thank you. Now I request our esteemed principal madam to deliver a presidential address on this August function. Madam.
Hello. Can you hear me? Thank you, Professor. So, can you hear me?
Yes, we can hear.
Okay.
We can hear you.
So, good afternoon, dear professors and students. I welcome all of you to this international webinar on two topics, current and future trends in electrocatalysis for energy production and nanosensors development, organized by the Department of Chemistry, CGAC Tirupur. I congratulate the head of the department, Dr. Rajagopal, the IQAC department coordinator, Dr. Sampath, organizers, Dr. Vijayan and Dr. Kaniyappan, for their collective effort made to organize talk on two very interesting and useful topics. A few words about the chemistry department. I would say with pride that our chemistry department is doing very well, both in terms of teaching and research. We have a wonderful team of professors who are very committed, dedicated, and always motivating and ready to help students. Though this pandemic has brought life to a halt, it didn't deter them from exercising their duties towards students. Without waiting for orders from the government, they had started the online classes for students right from the day the college was supposed to reopen. This sincerity is reflected from the results of the semester examination conducted by the Bharatiya University. There are university rank holders in UG and PG streams. Also, I must say that the research activities carried out by the department are excellent, and many of the research papers are published in high impact index journals like Elsevier, etc. So hats off to the entire group. Today we talk by Dr. Arunprakash Periyasamy, a PhD from the University of Surrey in UK, on an overview of electrocatalysis for feasible energy and fuel production, a topic which is apt for the current scenario. As we all know, the development of an alternative sustainable energy economy is now unavoidable due to the progressive and rapid depletion of world's reserves of fossil fuels and due to the increasing energy demands. Both these factors have started to take its toll on our planet. The combined effects of pollution and climate change caused by global warming add on to these issues. The result is an urgent need to develop a future world economy based on carbon-free and renewable resources. In this context, a lot of focus and studies are carried out on hydrogen, which is a high-quality energy carrier and an ideal candidate that can replace fossil fuels, thanks to its high specific energy density and clean combustion. To favor the worldwide utilization of hydrogen energy, the development of low-cost and sustainable energy conversion technologies like electrolyzers and fuel cells are required. So research work should be centered on providing key insights in achieving highly active, stable, and sustainable electrocatalysts for fuel cells and electrolytic hydrogen production. Such understanding will provide stimulus and boost future research to bring a hydrogen-based energy economy closer to realization. This is one example I have given. I am sure Dr. Arunprakash, who is the holder of 3 international patents with his wide exposure, would be able to attract you to this interesting and relevant research field through his talk. I wish him all the very best.
Thank you.
Similarly, nanosensor is another area which is gaining more attention. One of the first examples of a synthetic nanosensor was built by researchers at the Georgia Institute of Technology in 1999. It involved attaching a single particle onto the end of a carbon nanotube and measuring the vibrational frequency of the nanotube both with and without the particle. The discrepancy between the two frequencies allowed researchers to measure the mass of the attached particle. Since then, increasing amounts of research have gone into nanosensors, whereby modern nanosensors have been developed for many applications. Currently, the applications of nanosensors in the market include healthcare, defense, and others such as food, environment, and agriculture. Dr. C. Suresh, senior scientist at SEGRI, and one who has many awards to his credit, is an expertise in developing varieties of electrochemical sensors that served as electrocatalysts for numerous redox reactions. I am sure his talk would bring out some of the latest advances in this area and motivate you, and I wish him too all the very best. I would also like to mention that both Dr. Arunprakash and Dr. Suresh were students of government colleges for their basic degree, thus proving and setting an example that it is not necessary to qualify from renowned institutions to reach greater heights. The world has everything in plenty. It is up to us to grab the resources and opportunities and contribute through research something to save Mother Earth. Remember that if you stay positive, even in a negative situation, you win. So I hope this webinar would be very useful to all of you and you will be benefited definitely. I hope so. So thank you and have a nice day. Thank you.
Thank you, ma'am. Thanks for a wonderful presidential address.
Thank you.
Welcome to everyone. Now I'd like to give a short introduction of Dr. Arunprakash, one of our today's speaker. Dr. Arunprakash is from Udmalpet, Tirupur district, Tamil Nadu, India. He will be presenting a lecture on an overview of electrocatalysis for fusible energy and fuel production. He is currently working as a postdoctoral research fellow in Professor John Varco's group at Department of Chemistry, University of Surrey. He did his BSc Chemistry from Government Arts College, Udmalpet, and PG degree in Chemistry from Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore. Then he moved to Taiwan for his PhD. Dr. Arunprakash received his PhD degree in Chemistry with a specialization in Electrochemistry and Material Science from the National Taipei University of Technology, Taiwan in June 2011, under the guidance of Professor Sen Ming Chen. He was awarded the Taiwan government scholarship for pursuing his PhD degree. He is also a visiting academic fellow in the Sustainable Carbons Group of Professor Mehta at the Department of Chemical Engineering in the Imperial College, London. He worked as a postdoctoral research associate in the Advanced Sustainable Energy Materials Group of Dr. Anna Jude Sobrido at the School of Engineering and Material Science, the Queen Mary University of London from November 2018 to May 2020. He has worked also as a postdoctoral research associate in Professor Chang's Bio and Nanoanalytical Group at the National Taiwan University from November 2011 to 2018. He has published 43 research articles, 6 review papers, and 4 book chapters. He is holding 3 international patents, and he is currently the guest editor for the special issues Graphene-based Nanosensor and their applications for the journal Sensor, and Disordered Crystalline Material for the journal Crystals. His research focuses on the preparation of functional carbon nanocomposites, photoluminescent carbon nanomaterials, and semiconducting micro and nanostructured interfaces for biosensing photocatalysis, oxygen electrocatalysis, carbon dioxide reduction, and hydrogen evolution reaction. With this small introduction, I would like to invite Dr. Arunprakash to deliver for about 45 to 50 minutes of his lecture. Thank you, one and all. Dr. Arunprakash, you can carry on.
Okay, thank you. Good evening to everyone. Thank you for organizing this webinar. I'm very happy to join the webinar today, and I would like to thank Dr. Deepa ma'am, the principal of the Chikana College, for the nice introduction, and also the head of the department and the organizers for organizing this wonderful event. So I'm very happy to be part of this webinar, and the today's topic is electrocatalysis for feasible energy and fuel production. It's a wonderful topic, and energy and fuel production. So these are the recent trends or the future trends of the electrochemistry or energy field. So people are trying to find some alternate solutions to produce some alternate energy and fuels. So today in my talk, I'm going to introduce the techniques or what are the methods to produce energy and fuels through the electrochemical reactions. The main focus will be on the electrocatalysis. So before entering the topic, I would like to introduce you about the campus environment and career path. So I belong to my native is Udumilpet in Tamil Nadu, and I did my undergrads in Government Arts College Udumilpet and affiliated to Bharatiya University, and I did my MPhil and Masters in Sri Ramakrishna Mission Vidyalaya College of Arts and Science. So after completing my PG degree, then I moved to National Taiwan University of Technology to do my PhD in electrochemistry. So most of my PhD research focused on the electrocatalysis, and particularly for the development of nanomaterials for electrochemical sensors and biosensors. I think Dr. Suresh will be introducing you next after my talk about the nanosensors and electrochemical sensors. And after completing my PhD, then I moved to National Taiwan University for my first postdoc in electrocatalysis. So I started my research on electrocatalysis at National Taiwan University, and I did my postdoc in Professor Chang's lab, Bio-Nano-Analytical Lab. So where I have the opportunity to develop nanomaterials, sustainable materials for the fuel cell application and also for supercapacitor and water splitting applications. I have also developed some photocatalyst during that period. So after completing my first postdoc, then I moved to Queen Mary in the year 2018 to carry out my second postdoctoral research on zinc air batteries, metal air batteries. So during this period, I tried to develop nanomaterials or sustainable electrocatalysis using carbon materials. So I have worked on several carbon materials like carbon nanotubes, graphene nanotubes, graphene and graphene carbon composites, and different carbon structured materials like 1D and 3D structured materials for metal air batteries. So recently I have got a position in University of Surrey, and starting from next week, I'm moving to University of Surrey, and I'm also working as a visiting academic fellow at Imperial College London. So all this gives many researchers and students and faculty members will be watching this talk, and I would like to give you the motivation that as the principal ma'am pointed out, that it is doesn't matter where you study your undergrads or postgrads. So you should aim for those high level of you should have some high aims and aim high, and then always set goals which you can achieve, and then dream high. Then definitely you can achieve more in your life, and everyone can achieve in academic career, whether you go for research or arts or science, it doesn't matter. But do whatever you do with dedication, and with dedication and hard work, everyone can achieve. So don't let anyone to bring you down. Be yourself and ignore the negativity. Stay positive. So with positive thoughts and with good people around you, like good teachers and good friends, definitely you will have a good career. So take this motivation from my talk, and keep the good work, hard work, and definitely you all can achieve. So especially those who studying at Chikana College, aim high. Don't think you are studying in a government college. Always people who studied in government college have achieved more. There are a lot of examples. So be positive and work hard. Definitely you can achieve. So next time, straight away moving into my topic, electrocatalysis. So everybody know about the catalyst, like whoever working on the inorganic chemistry or organic chemistry, people used to develop the catalyst. So catalyst are the materials or the chemicals which drive a reaction, particularly chemical reaction. If you see the normal catalyst, those who use organic chemist will develop some organic catalyst, like organic compounds they will synthesize in the lab, and they will use it for driving some organic reactions. So electrocatalysis, so the catalyst material used for driving some electrochemical reaction is called electrocatalysis. So the electrocatalyst and catalyst have some common features. That is, the catalyst material should not be consumed during the reaction. So the catalyst material should be highly stable during the reaction, and it should have high turnover rate or turnover frequency. That means number of molecules or number of products produced per active site or per unit area. So these are all very important, or the common features between an electrocatalyst and catalyst. So electrocatalyst means a catalytic material that can drive an electrochemical reaction, and similar to a catalyst, it will increase the reaction rate or kinetics of a reaction. So there are different types of catalyst materials, like homogeneous catalysis or homogeneous electrocatalyst, immobilized electrocatalyst, and heterogeneous electrocatalyst. So what are the difference between these catalysts? For example, in the case of a homogeneous catalyst, it is a molecular catalyst, like porphyrin molecules or cobalt-based molecular catalysts are developed for various electrocatalytic reactions. These molecules will be introduced into the electrolyte. So as an electrochemist, or those who are working on electrochemistry will be well aware of this fact, that you will have an electrochemical system that consists of electrochemical cell, and you will have an electrode, electrolyte, and the reactant molecules. So in this case, for example, in the case of homogeneous catalysis, the molecular catalysts are mostly used. The molecular catalyst will be introduced into the electrolyte, and it will react on the electrode surface. What is the purpose of the electrode? The electrode is a conducting material, and it helps to shuttle the electrons between the electroactive molecule and the electrode. So in this way, you can promote the electron transfer. The material which you are going to use for electrode, which you can use as electrode, should be highly conductive. The metals like copper or aluminum are mostly glassy carbon electrodes people used to use as electrode. Also, you can use nickel foam or conductive materials. So these molecular catalysts will be introduced into the solution, and because of the electron transfer, it can form some product. So in the case of immobilized electrocatalyst, the electroactive catalyst will be immobilized on the electrode surface, either through some covalent interaction or physical interaction. You can tether or you can functionalize on the electrode surface. So in this way, you can immobilize your catalyst on the electrode surface. It gives additional stability. Suppose if you are having your electrocatalytic material in the solution, it is free to mobile or free to diffuse. So it will have some mass transport limitation. Whereas if you immobilize your electrocatalyst on the electrode surface, it is highly stable. So people try to develop immobilized electrocatalyst as well as heterogeneous electrocatalyst. So heterogeneous electrocatalyst means the difference is the electroactive material will be immobilized and it will have an interface. That is, the electrode is a solid material and your catalyst will be solid as well, and you will have an electrolyte. In some reactions, you will also have some gas like oxygen or nitrogen or carbon dioxide. So it will be a triple phase or triple point, solid, liquid, and gas interface. That is called heterogeneous. So in this case, the reaction will be happening at the interface of the electrode and the electrocatalyst with the transfer of electrons, and the product will be formed. So you have to bear in mind in this, during the heterogeneous electrocatalysis, adsorption of the reactants and also the desorption of the products will be the main determining factors. In the heterogeneous electrocatalysis environments, as I told, solid liquid interface plays a major role. Whether it is a battery or in a electro water splitting device, solid liquid interface plays a major role. And even in batteries, you may observe some solid SCA formation in the interface. Solid polymer interface. People also try to use some conducting polymer materials. They modified on the solid electrolyte electrode to increase the conductivity. That is called solid polymer interface. Any kind of polymer, it should be highly conductive, like polypyrrole or polyaniline can be used as a conducting. These conducting polymers can be used to modify the interface. Gas solid electrolyte. So like carbon dioxide reduction or oxygen reduction reaction, you will have gases like the reactant molecules will be in the gas phase, like carbon dioxide or oxygen. It will react on the electrode electrolyte interface and it will generate product water. For example, in the case of oxygen reduction, it will yield water. So in the case of carbon dioxide reduction, it will yield n number of products like C1 to C4 products. Like it can form methanol, ethanol, propanol. Like these are the simple aliphatic alcohols. It can also form various different molecules. These are the two steps involved in the difference between homogeneous catalysis and heterogeneous catalysis. The reactants will be introduced into the electrolyte and adsorption will be happening, and then it will form an intermediate and the product will be formed from the catalyst will be regenerated again. This is in the case of homogeneous catalysis. There is no immobilization of the catalyst on the electrode surface. Whereas in the case of heterogeneous catalysis, the catalyst substrate, the surface, the electrode surface will be modified with the catalyst, either through covalent cross-linking or some physical interaction. The catalyst can be modified by using some binders like naphthalene. People used to use naphthalene and they prepare the catalyst as a ink and they will modify on the electrode surface and it will give additional stability. So in the case of heterogeneous catalysis, since the catalyst is immobilized, the reactants are free to diffuse from the electrolyte and it will get adsorbed on the catalyst surface. So the adsorption energy of the reactants and the intermediates and products are the key descriptors of the electrocatalytic activity. So I hope you get a clear idea about the difference between electrocatalysis and the general catalysis, that is the organic catalysis or whatever catalysis people working on. So electrocatalysis, in this case, the reactants will be adsorbed on the electrode surface and the adsorption energy is very important. As I told, the four important points to note are: one of the reactant approaches the catalyst surface and it will adsorb on the active sites. So you will have a catalyst immobilized on the electrode surface, but all the surface area will not be active. Only those active sites located on the catalyst will be highly active for a particular reaction. So tuning the number of active sites is very important in electrocatalysis. Once one reactant is approaching the active site, then another reactant will also tend to approach the catalyst. So in this way, like n number of reactants will be continuously approaching the reactant site or active site, and rearrangements of electron takes place. In the case of electrocatalysis, you need to supply energy in the form of potential or current. When you supply this energy, they are acting as driving force. In that way, electron transfer will be happening. In this case, heterogeneous electron transfer will happen at the electrode interface. The products are released from the surface after desorption. So adsorption and desorption energy are very important in the case of determining the electrocatalytic activity. For example, free energy. So free energy is the Gibbs free energy. It's when it is negative, it is the reaction will be spontaneous, that we all know. And for example, there will be some energy barrier or activation energy. Every reaction needs some activation energy or to overcome the energy barrier. Then only if you supply that energy only, the reactant will be converted to product. So you have to supply some energy higher than the activation energy or the energy barrier. So it will also form the intermediate. So without catalyst, this activation energy will be much higher. When you have a catalyst, then you can minimize the free energy for that reaction, and the reaction will be much more spontaneous. So there is another term called bioelectrocatalysis. What is mean by bioelectrocatalysis? Bioelectrocatalysis means some biological molecules will be utilized as the catalyst. For example, enzymes. Enzymes are very specific for a particular reaction, like enzyme-based biosensors. They immobilize some enzymes on the nanomaterial surface. You can't immobilize an enzyme on a bare electrode surface. For that, you need a nanomaterial, and then you need to immobilize that enzyme, particular enzyme. It can be any enzyme like glucose oxidase for oxidation of glucose, and oxidase peroxidate for hydrogen peroxide reaction. It depends on the substrate. So enzymes are very specific to a particular reaction and a particular substrate. For example, in the case of the bioelectrocatalysis, enzyme needs to be used. There are various types of redox enzymes or oxidoredox enzyme. You can use any enzyme, and the reactants will be converted to products. Without enzyme, the activation energy will be higher. With enzyme, the activation energy can be lowered. The activation energy with enzyme will be much more lower or lesser than without enzyme. Overall, the energy released can be also calculated. So this is the reaction coordinate and energy. So next, let's see about the electron transfer process during electrocatalysis. So the electrochemical reaction or electrocatalysis occurs in a half cell reaction. So we often used to say half cell and a full cell. Half cell reaction is a reaction which happens in an electrochemical cell which has 3 electrodes: working electrode, reference electrode, and counter electrode. The working electrode is made of glassy carbon or any conductive metals. It should be highly stable in that potential window. And reference electrode is the material or the electrode which helps to measure the potential with respect to the working electrode. Always bear in mind, the working electrode should be highly stable, and its potential should be maintained at 0. It should not change when you are doing some electrochemical reaction. Because of this reason, no current will be flowing through the working electrode. The current flow will be happening through the circuit from working to counter electrode. So in a half cell, you will have 3 electrodes. One is working electrode and reference electrode. The purpose of the working electrode is the material or the conducting material on which your electrochemical reaction of interest will happen. And reference electrode is used to measure the potential of with respect to the working electrode. And counter electrode is for the control the flow of electron or to complete the external circuit. So you will have an electrolyte in the solution. So as a conducting for conducting ions. This is the electrochemical setup, and the working potential window depends on several things like pH of the electrolyte and also the type of electrolyte, like aqueous electrolyte or non-aqueous electrolyte. And based on the type of electrolyte also, the potential window can vary. For example, in the case of sodium chlorate, the potential window will be from 2 volt, whereas if you use some ionic liquids, you can extend the potential window to 3 volts. So based on the electrolyte, you can tune the working potential window. In the case of batteries, we always need a more broad wide potential working window. In the case of electrocatalysis or some nanosensor, you need some minimum potential window, like within 1 volt you can do that process. For example, for water splitting, you need much higher potential window like 1.23 or 1.3 volt, because the thermodynamic potential for splitting water into hydrogen and oxygen is 1.23 volts. So you need to supply some energy higher than that. So we have to focus on these things like the type of electrolyte, electrolyte species, pH for determining the working potential window. So this is a simple cyclic voltammograms, and it has 2 segments, forward and reverse scan, and you can record the cyclic voltammograms to understand the electron transfer process. The one direction will be for oxidation purpose and the other one for reduction purpose. If you are scanning towards a negative potential, it is called reduction, and if you are scanning towards a positive potential, it is called oxidation. The peak in the reduction potential region is called reduction peak, and the peak in the oxidation potential is called oxidation peak. So if you have, this is called a reversible redox process, and it will give you an information about how many number of electrons are transferred. For example, the blue curve is the curve recorded in nitrogen environment, whereas this is the one curve recorded in oxygen environment. It undergoes one electron transfer process, whereas here 2 electron transfer process will be happening. So multiple electron transfer process will happen, and based on the number of electron transfer, your product will vary. So the role of electrode-electrolyte interface in electrocatalysis. So you will have an electrode and an electrolyte. So you will form an electrode-electrolyte interface automatically, and diffusion of the electrolyte or the reactant molecules will happen in the solution. So this is called heterogeneous electron transfer. In the this picture will give you an idea about the Helmholtz layer or Helmholtz double layer. In electrochemistry, we used to say a double layer will be formed at the junction of the electrode and liquid junction, and it will be constituted by oppositely aligned ions, and this is called the highly oriented dipoles. So the dipoles will be positive and negative charge, and you will have highly oriented dipoles in the solution next in the layer next to the electrode. That is called inner Helmholtz and outer Helmholtz. It will be few Armstrong thick, and you will also have solvated ions. The ions will be surrounded by water molecules, that is called solvated ions. So this will be happening in the electrolyte and liquid and electrode interface. So oxidation and reduction reaction can happen at the electrode surface depending on the electron transfer. When the electron is accepted, reduction process will happen. When the electron is released from the electrode, then oxidation process will happen. So the reactant and product will be generated on the electrode surface with the absorption of the reactant and the release of the product. We have to consider the free energy for each absorption of the intermediate. This you can obtained from DFT calculation. This information will be very useful for determining the mechanism. Charge transfer and mass transfer at the electrode surface. Electron transfer will occur at the electrode. So we often say we call it as charge transfer. And what do you mean by mass transfer? Mass transfer is the transport of the ions or your reactant molecules from the bulk electrolyte to the electrode surface. That is called mass transfer. 3 types of charge transfer. One is charged species transport, and the neutral species transport, and momentum transfer. These can happen in the electrode-electrolyte interface. Mass transfer is a very important property, and you need to control the mass transfer by rotating or stirring your electrolyte to ensure the efficient transport of reactant from the bulk solution to the electrode. And also charge contribution. There are 2 types of charge contribution. One is called capacitive charge contribution, and the other one is called Faradaic charge contribution. Whenever electron transfer happens between the reactant molecule and the electrode surface, it is called Faraday charge transfer. Whereas if there is no direct charge transfer between the reactant molecule and the electrode interface, then it is called capacitive charge transfer. So simply the reactant molecules will tend to, the oppositely charged molecules will align on the electrode interface without charge transfer. That is called capacitive charge transfer. So whenever electron transfer happens, means it is called Faraday charge transfer, and there is no electron transport, but only the capacitive contribution, means only the oppositely charged ions will form a double layer at the electrolyte interface. So simple difference is electrode at the electrolyte interface, if a double layer is formed, it is called capacitive contribution. There is no double layer formation and only electron transfer, then it is called charge transfer. So the charge transfer information you can get from cyclic voltammetry and particularly from impedance spectra. This semicircle will give you an idea about the charge transfer. So the impedance spectra is usually plotted against the real part of the impedance and imaginary part of the impedance, and the semicircle diameter will directly give you an idea about the charge transfer. If the semicircle diameter is larger, it means the resistance is higher. If the semicircle diameter is smaller, then it means the charge transfer resistance is minimum. In this case, you can observe the semicircle diameter is 0.25. So the charge transfer resistance is minimum. Also, in some cases, you can also observe some inductive loop due to the adsorption of the intermediate. Other than this process, electrolyte flow, molecular ion diffusion, and redox reaction can also happen. So we have to bear in mind all these things when dealing with electrocatalytic reactions. In this picture, you can observe the transport of the electrolyte species, like for example, like carbon dioxide and also water molecules through the porous substrate. So if you have a porous surface, then the transport will be much more efficient. And fundamental kinetics. So far, I have discussed with you about the electrocatalysis, bioelectrocatalysis, and what is meant by charge transfer, mass transport, and also there are three ways of mass transport. This is called fundamental kinetics. So the three types of mass transport are generally called as diffusion, migration, and convection. So diffusion is the transport due to concentration gradient. What is meant by concentration gradient? So in your bulk electrolyte, you will have much more higher concentration, whereas near your electrode interface, the concentration of the reacting species will be much lesser. So there will be a concentration gradient between your bulk solution and your near the electrode-electrolyte interface. For instance, the reactant molecules from the bulk solution tend to move toward the electrode surface from higher concentration to lower concentration. As a result, a concentration gradient will be set up. So the transport of reactant molecules governed by concentration gradient is called mass transport, whereas the transport of reactant molecules governed by potential, for example, potential gradient. If you are applying a positive potential or negative potential, then the cations will move towards cathode and anions will move towards anode. It depends on the potential which you applied or the potential gradient which you are creating. So this is called migration. And convection, you are stirring your solution and you are generating some flow in the electrolyte, and because of the generated or induced flow or the motion of the molecules will change, that is called convection. So these are the three types of transport which occur in during electrocatalysis. Mainly we have to focus on all these types of mass transport when you are doing an electrocatalytic reaction. Heterogeneous electrocatalytic reactions for energy and fuel production. So there are several types of electrocatalytic reaction which are very useful for energy and fuel production. The main reaction which are useful for energy production are ORR, OER, and also fuels you can generate from CO2 reduction. Through water splitting, you can produce fuels like hydrogen and oxygen. So hydrogen is a very green fuel because it has zero emission. Like other hydrocarbon fuels, when you burn hydrocarbon fuel, you will end up with carbon monoxide. When you burn hydrogen in a hydrogen fuel cell car, you will end up with water. So it is economically viable, and it is also a very sustainable and green fuel. So these are the important electrocatalytic reactions: CO2 reduction reaction, oxygen reduction reaction, and oxygen evolution reaction. Oxygen reduction and oxygen evolution reaction are called oxygen electrocatalysis, whereas hydrogen evolution reaction is called hydrogen electrocatalysis and CO2 electrocatalysis. These are the very important reaction which plays a major role in the energy devices like fuel cells, rechargeable metal air battery, and also water splitting energy devices like PM fuel cells and PM devices. There are different types of materials are used for electrocatalysts, like graphitic carbon, graphene, carbon nanotube. These are the carbon materials which are used as carbon support or carbon-based electrocatalysts. So the thickness and dopants. Dopants means heteroatoms. You can use a non-metal like nitrogen, boron, phosphorus, sulfur. By introducing these heteroatoms into the structure of the graphitic structure of the carbon material, you are inducing some change in the electronic configuration, and also you can introduce some defects. Because of that, the electrocatalytic properties or the conductivity will change. So the carbon supports or carbon materials are used as electrocatalysts. Also, like metal-based catalysts are also available. The best well-known materials are noble metals like platinum, palladium, ruthenium, gold are commonly used as noble metal-based electrocatalysts for all these reactions. You can also use non-noble metals like transition metals like iron, cobalt, nickel, copper, and tin. These are relatively inexpensive compared to noble metal. For instance, platinum cost is very high, like $100 US per even a milligram or so. But whereas when you go for iron or cobalt, electrocatalytic. It is very inexpensive, and you can produce from in your lab. So scaling up the reaction is very easy in the case of when you are dealing with a transition metal catalyst rather than a noble metal based catalyst. You can also design different shape or structure like carbon shell and metal core. Metals always tend or prone to corrosion in the acidic or alkaline environment. You can protect the metal active sites by forming a carbon shell. In that way, you can increase the stability. You can also introduce some third component like iron carbide, cobalt sulfide or phosphide or carbide. These are very good for evolution reactions like hydrogen evolution and oxygen evolution reaction. So oxidation and reduction, by these two methods, you can produce energy and fuel. There are different types of reaction like ammonia reduction and hydrogen peroxide reduction and chlorine or methane evolution reaction, and also water oxidation, ethanol oxidation. Alcohol oxidation is also very important in the case of fuel cells like direct methanol fuel cells, and also chlorine oxidation is also industrially very important. And nitrogen reduction, usually ammonia will be produced by Haber's process. Instead of Haber's process, we can use some electrocatalysis. You can undergo nitrogen. You can convert nitrogen into ammonia easily, and also water reduction and oxygen reduction. Mostly noble metals are used. So people are trying to develop some sustainable electrocatalyst, and we are trying to replace the noble metals by developing some inexpensive electrocatalyst. Sustainable hydrogen fuel production plays a major role. Photoelectrochemistry and the electrocatalysis is also playing a major role in producing the sustainable fuel hydrogen. Like we can use solar integrated systems also to produce the hydrogen fuel. Mostly people are trying to produce hydrogen from biomass, which is a sustainable precursor, and we can produce hydrogen. So the hydrogen storage can be done using different kind of porous material, and it can be used for transportation. This picture shows you an idea about natural water splitting. So this is the Pacific Ocean and Atlantic Ocean, where the region at which both these oceans meet, literally they have different colors. It is also called as water splitting, but not chemical water splitting. So in lab, we are trying to do electrochemical water splitting. By supplying electrical energy, we are trying to split water into hydrogen and oxygen. So the energy devices like energy storage and energy conversion. So the energy storage devices like supercapacitors or fuel cells, and also energy conversion devices like PM electrolysis cells are playing major role in boosting the economy. And there are two types of reaction: oxidation and reduction, like water oxidation and also water reduction reaction. Is playing a major role in producing this energy and fuel. For example, in the case of electrochemical water splitting, you need two electrodes, and you have to supply an over potential higher than the thermodynamic potential, that is 1.23. Well, you can connect to a 9 or 12 volt battery, and with the transfer of electrons, these process, the splitting of water will happen, and the hydrogen will be evolved at the anode, and hydrogen and oxygen evolution will happen. Hydrogen evolution will happen at the cathode, and oxygen evolution will happen at the anode. Some bubble generation will be occurring at the both anode and cathode. The main difference between the PM electrolysis cell and fuel cell is, in the case of PM electrolysis cell, the feeding substance or the electrolyte is water. By using the green electrolyte water, you can produce hydrogen and oxygen. Whereas in the case of PM fuel cell, you have to input hydrogen and oxygen. So the PM electrolysis cell and fuel cell can be combined together. The hydrogen and oxygen produced in the electrolysis cell can be fed into the fuel cell to produce power or energy, and water is the output. So these are the green energy devices. They use only water. That's why they are gaining more and more attention recently. So why we need to develop nanostructured materials? Why nanostructured materials are needed for electrocatalysis? In this slide, I have shown the different types of nanomaterial which are used for carbon dioxide reduction. So carbon dioxide can be reduced to form different products like ethylene, ethane, methanol, and different carbon products, C1 to C4 products. So particle size effect is very important. For example, in the case of gold nanoparticle, there are different size nanoparticles like 4 to 10 nanometer. The black one is for the 4 nanometer. So compared to the larger particle, the smaller particle have more number of active sites and they are performing well. And also Faraday efficiency also can be tuned based on the particle size. And defects and anisotropic effects. So nanomaterial can be any size, like a particle sphere, like an octahedra, cube, or a nanowire, nanorod. So we basically classify the nanomaterial based on their anisotropy or their orientation, like zero-dimensional material, one-dimensional material, two-dimensional material, and 3D material. If you go for 3D material from zero-dimensional material, then you will have more pores in the structure. Because of the more available number of pores, the mass transport and electron transport will be much more efficient. In this picture, you can observe the nanowire edge have more number of active sites than the nanoparticle edge. So based on the morphology, based on the orientation, you can control the activity. Oxide derived material, like the copper based material like copper oxide, cuprous and cupric oxide also have high activity towards CO2 reduction. Like the intrinsic copper oxide, also the copper oxide which you prepare by electrochemical method or by hydrothermal method also performs well. So the copper-based electrocatalyst has been introduced first by Hori et al. And following that, lot of works have been going on in the field, like Dr. Kannan's group also doing lot of work in CO2 reduction electrocatalysis. This is gaining more attention compared to the polycrystalline copper material. Nanomaterials are playing major role. Structure-activity relationship. So structure-activity relationship means depending on the structure, you can control your activity. So depending on the structure, you can also control the selectivity. So there is a relationship between activity and selectivity with structure. By tuning the structure, you can control the activity and selectivity. For instance, if you have a platinum gold alloy, it produces only 5 milliampere per centimeter square current density in oxygen reduction reaction. Whereas if you have a platinum palladium alloy with 111 phase, then it produces 15 milliampere per centimeter square. So instead of forming an alloy with gold, if you form an alloy with PD, it is good for oxygen reduction reaction. Similarly, when you form platinum rhodium, platinum iridium, platinum ruthenium, the activity trend decreases. So based on these trends, you can form the alloys, and based on the structure, you can control the activity and selectivity. Also in the nitrate reduction, like you can form different, like hydroxylamine, and also you can form tetraammonium ion and nitrate. So different products can be possible based on the structure and also the composition of the alloys. This picture gives you a clear idea about what is meant by an alloy and how it can influence the activity. For instance, the platinum nickel alloy performs much more, like 4 or 5-fold better than the commercial platinum catalyst. Like platinum can be alloyed with the platinum yttrium, gadolinium, and also different lanthanum series metals you can use. They are inexpensive, and also you can use transition metals, and you can form an alloy to increase the activity. Different strategies have been used, like nanostructuring and support and shape and adsorbance and core shell or alloy structure. You can control the activity. And particle size effect. By controlling the size of the particle from 1 nanometer to 100 nanometer, always if you have a smaller size particle, you will have more higher electrochemical surface area and more number of active sites that will increase your activity. And based on the shape, like octahedra to nano channels, like nano frames performs better than the solid particles. So creating the pores is very important in electrocatalysis. Based on the crystal planes also, the electrocatalytic activity can be influenced. And also based on the transition or alkali metal ions also, present in the electrolyte, you can tune the electrocatalytic activity. Like the material selection, electrolyte selection, potential window selection, all matters. And also the structure. For example, if you have a commercial pure platinum particle compared to the solid particle, platinum nanowires perform better. And also PTPB nanoplatelets like lead and platinum alloys performs better. Why we need to tune the active sites? As I pointed out earlier, active site is the particular site of interest where electrocatalytic reaction will happen. So if you introduce more number of active sites, then the electrocatalytic reaction can be activity or the kinetics can be improved. In this picture, you can observe there are different sites on a particle like ethylene site, ethanol site, and propanol site. For example, if you are interested in producing ethanol, then you can create, or propanol, then you can create more number of ethanol site, and also you can create more number of propanol site on an oxide derived copper. Instead of having everything, then it will affect your yield. For instance, if you have 20% of ethylene site and 50% of propanol site and 30% of ethanol site, you will not have high activity. In that case, you can have more number of ethanol or propanol site based on your requirement. So active site engineering is very important. How to tune the active sites for electrocatalysis, how to maximize the use of active sites. This can be done by shortening the distance between the alloys or the metals present in your alloy. If you have palladium and nickel, then if you shorten the distance between these two metals, then you can increase the number of active sites. Also, you can do active site engineering like introducing the defective sites, nitrogen moieties, single atom catalyst, and oxygen vacancies, and crystal facets and interfaces. A lot of things can be done by engineering the active sites, and you can improve the activity. What is meant by active site engineering? Controlling the density of active sites per unit area is called as active site engineering. This can lead to structural effect control and also contribution of atoms with lower coordination number. If you have more number of lower coordination number and defects, then you can increase the activity. Also, the electrochemical interfacial properties and electrolyte composition can also be influenced. So you have to consider all these when you are doing active site engineering. So like overlayers or multi-layer on a catalyst surface, you can create a single monolayer or multi-layer, and based on the number of layers, you can control the surface energy of your electrocatalytic reaction. This can also be done by tuning the electronic structure, hierarchical morphology, and electrode interface. The number of active sites increase will lead to increase in the electrical conductivity, and the reaction barrier can be lowered. For instance, in the case of molybdenum sulfide, if you introduce a vacancy and strain, the activity for hydrogen evolution increases. Different strategies can be used like catalysis, performance, and vacancy. You can knock out oxygen from the metal oxide surface, and you can create an oxygen vacancy. You can knock out a metal or an anion or a cation from the surface, and you can create cation and anion vacancy. So whenever you introduce a vacancy or defect, it can also increase the activity. Increasing the coordinatively unsaturated sites can also lower your surface energy, and it can also increase the activity. So optimizing the absorption energy of the intermediate is very, very important. If you have a minimum absorption energy, then the activity will be much higher. The current trend or the recent trend is preparing bifunctional electrocatalyst, a single electrocatalyst which can perform dual roles. Like a single electrocatalyst can catalyze both ORR and OER. This is called bifunctional electrocatalyst. There are also trifunctional catalysts which can do hydrogen evolution, oxygen reduction, and oxygen evolution reaction. The other type of bifunctional electrocatalyst, this is called bifunctional oxygen electrocatalyst. Similarly, bifunctional hydrogen electrocatalyst for hydrogen evolution reaction and also for hydrogen oxidation reduction. Different strategies are available. You can refer to the literature, and you can choose the best method for preparing a material. Like electrochemical dealloying, you can apply a particular potential. For instance, if you have a platinum palladium, you can leach out some palladium atoms by applying some oxidation potential, and this is called electrochemical dealloying or leaching. In that way, you can create some pores in your alloy. This can also lead to improved kinetics. And surface engineering and interface engineering are also playing major role. You can use metal oxide or hydroxide and metal organics based substances. How to control the particle size, shape, and crystal facets? There are several ways to control the shape and size of a particle and crystal facet. This can be done by adjusting the solution pH, acidity and basicity, and synthesis temperature, and also capping agents. So a capping agent is a substance which will cover a metal ion when it is nucleating, and it will suppress the growth of the particular particle in one direction. For instance, if you want to grow a nanowire in 111 direction, then you can use a particular capping agent. If you want to grow a octahedra shape or cube shape, then you can go for different capping agent. So by selecting different capping agent, you can control the growth of the nanomaterial and reducing agent concentration. So concentration effects have a major role in controlling the shape of the particle, whether it is a nanowire or whether it is a icosahedra or octahedra shape. You can control by adjusting all these parameters. And interfacial effects in supported catalyst for electrocatalysis. So supports always have a major role. So when you have a support, then you are increasing the stability. Carbon materials are mostly used as the supports for the nanomaterials. The well-known carbon supports are carbon nanotubes, graphene, 1D material and 2D material. This can be done by 3D printing and also electrospinning. So in that way, by tuning the interfacial effects or by tuning the properties of your conductive support or carbon support, you can tune the interfacial properties. The activity about electrocatalytic activity can be determined from volcano plots. The minimum energy or the metal with minimum absorption energy performs well. For instance, platinum, nickel, and platinum yttrium have minimum energy and they perform well. And also the positive and negative potential, this is water splitting or bifunctional electrocatalysis, and the potential for the thermodynamic potential is 1.23. Whatever potential you apply higher than that is called over potential, and in that way, by minimizing your over potential, you can increase the production yield. This is a simple water electrolyzer with anode and cathode. Hydrogen evolution will happen at the cathode and oxygen evolution will happen at the anode, and you can collect the gases very easily. You can also integrate with the solar system like solar panel, and this is called PEC water splitting, photoelectrochemical water splitting. So multi-component heterostructure engineering, these are all different strategies. All these strategies are used to control the adsorption and desorption of the intermediate. So you have to get this information through DFT calculation, and you can design a system which have minimum adsorption energy, then you can have better activity. What are the best catalysts for electrocatalyst for hydrogen evolution? What are the best materials for oxygen evolution and oxygen reduction reaction? The best benchmark for ORR and OER is platinum and palladium. Also for hydrogen evolution, the best material is ORR, and molybdenum sulfide is the inexpensive material. People try to develop carbon-based composites like they alloy with some metals like other metals like woodsite or different metals can be used, and based on the structure also you can tune the activity. For oxygen evolution, oxides and hydroxide are very good material, and perovskites are very good materials for oxygen evolution. And hydrogen evolution reaction mechanism and hydrogen evolution and oxygen evolution reaction mechanism. So whoever working on oxygen electrocatalysis and oxygen and hydrogen electrocatalysis, please pay attention to this mechanism. For instance, in the case of hydrogen evolution, 3 types of steps are very important mechanistic pathways. That is Volmer reaction, Havrosky reaction, and Tafel reaction. These are very important reactions. In the case of HER and OER in alkaline condition, adsorption, desorption, and recombination process are playing major role. And the oxide bond formation is playing a major role in the oxygen evolution reaction mechanism. So ORR mechanism in acid and alkaline, as I pointed out before, the double layer will be formed, and based on the where your oxygen molecule is bonded or at which position it is bonding, it can determine your inner sphere mechanism or outer sphere mechanism, whether it is acid or alkaline. Whenever you have an oxygen molecule adsorbed directly on the electrode surface, then it will contribute to the inner sphere mechanism, and it can reduce oxygen directly to water without forming hydrogen peroxide. Then it is in the outer sphere or outer Helmholtz plane, then it will generate the hydrogen peroxide. The oxygen adsorption models also play a major role, and the direct bonding model, Pauling model, is the best one because it minimizes the hydrogen peroxide yield during the oxygen reduction. So oxygen adsorption also matters in oxygen electrocatalysis, and this is called volcano plot. As I told before, platinum and palladium are performing well because they have a minimum adsorption energy, and also the adsorption energy for the hydroxyl ion is also minimum for platinum. Because of that, it performs well in the ORR. By forming some platinum cobalt alloy, or by alloying platinum with nickel and cobalt with the platinum skin, you can minimize the oxygen binding energy. So oxygen binding energy and hydroxyl binding energy are very important. You can predict easily the oxygen reduction mechanism by a rotating ring disc electrode, and based on this, experiment you can determine the hydrogen peroxide yield. Electrochemical reduction of carbon dioxide, it will generate lot of products. So because it is a multiple electron transfer process rather than ORR or OER, it is a multiple electron transfer process. Each product will have a different absorption energy. So we have to consider all these energy like methanol, ethanol, formic acid can be produced. And electrochemical cell setup is very important for all these reactions, whether it is a half cell or full cell. You should separate your electrodes, and also you should have a static flow or a circulated flow to improve the mass transport, and gas diffusion electrodes where the gas can be directly fed to the catalyst surface can minimize the mass transport limitations. So the gas diffusion electrodes always have much more higher advantage than the aqueous phase electrodes, because the gas molecules are directly fed to the catalyst surface without the need for the gas molecules to diffuse through the electrolyte. The gas stream and electrolyte stream should be separated, and it can help overcome the pH limitation, and it can help for the CO2 transport. The choice of electrolyte is very important: aqueous electrolyte, non-aqueous electrolyte, and imidazole cation. So if you use aqueous electrolyte, the potential window will be very minimum, and if you have non-aqueous electrolyte, the potential window can be increased. And when you add imidazole cation, that is ionic liquid, you can increase the conductivity. And mass transport limitations you have to consider, and the surface of the electrode should be rough or porous. That can also affect your diffusion and concentration profile. You have to bear this in mind. And mostly in CO2 reduction, copper based materials are used. The main reason for this is copper have the unique ability to reduce CO2 to 2 electron products. Negative absorption energy, this is the only metal with a negative absorption energy but a positive absorption energy for hydrogen. That's why people are using copper as a catalyst for CO2 reduction. Different mechanism happen in aqueous electrolyte, ionic liquid, and also non-aqueous, and both non-aqueous and aqueous. So we have to pay attention to every type of mechanism, and then you have to select the electrolyte based on that. And we can go for in situ techniques like FTIR, Raman, where you can monitor the products formed during your reaction directly. So in situ monitoring of the products or reactants will give you some clear idea about the mechanistic pathways. And efficient electrocatalyst, like controlling the morphology and also the dimension from 0 dimension to 3 dimension. You can tune the porosity. In that way, you can increase the active site surface area, conductivity, mechanical strength, and electrocatalytic activity. So surface engineering is very important in electrocatalysis. So this is the recent trend. People are trying to develop single metal atom catalyst. Instead of having a nanoparticle with 50 nanometer or 100 nanometer, people are trying to develop a metal organic frameworks that can be carbonized, and it can be generate dual atom catalyst or single metal atom catalyst. In that way, the single metal atom catalyst means it will be 1 nanometer size diameter. So 1 nanometer means very, very, very less, and you have n number of sites in a particular area. In that way, you can increase the number of active sites. And this is a big challenge or a future goal for electrochemical water splitting water or using seawater to produce hydrogen and oxygen. This is our future goal, and we have to focus on reverse. In this integrated system, we should have reverse osmosis and also common electrolyzer combined with some photovoltaics. So this is a big challenge, and it will need a lot of energy to produce this one. In that way, by doing so, we can generate a lot of products, and these are the electrosynthesized chemicals, what can be produced and what are the market value. This will give you a clear idea about what are the important chemicals like formic acid, carbon monoxide, ethylene, and ethanol. These are the vital chemicals produced during CO2 reduction, and they have a very huge market value. But there is a big challenge. We need to achieve 500 milliampere per centimeter square. This is the industrial grade current density benchmark, and the electrolyzer cost is $300 per kilowatt. We have to minimize this. This is the planned lifetime for another 30 years. So this is the future goal. Finally, coming to end of my presentation, the take-home message from my talk. The material selection plays a very major role, and it has a great influence on the electrochemical activity and stability. So increasing the porosity and surface area and electrochemical surface area or electrochemically active surface area increases the conductivity and mass transfer during electrocatalysis. Understanding the catalyst degradation mechanism is very important for improving the stability, and the stability and carbon corrosion of materials should be assessed from core batch diagram. Care must be given while evaluating the porosity and electrochemical surface area, and 3D printing has huge prospect for the development of PGM, that is platinum group metal-free porous carbon catalyst for water splitting purpose. And finally, coming to the end of my talk, I would like to introduce a special issue which I am currently guest editing, graphene-based nanosensor and the application for the journal Sensor. The most of the this special issue will be focused on the papers or the review articles based on graphene-based nanosensors. So all the publications or all your submissions are welcome for this special issue. Finally, I would like to conclude my talk and acknowledge the few people who have supported me a lot during my career, especially my PhD supervisor, Professor Chen, and also the postdoc supervisor, Professor Chang from National Taiwan University, and also the two professors from Dr. Anna Sobrido from Queen Mary University of London, and also Magda Titrici from Imperial College London for supporting me during my postdoc career, and currently Professor John Warko at University of Surrey for the postdoc position which he has offered recently to me. And thank you all for your kind attention. Thank you.
Thank you, Dr. Arunprakash. It was a wonderful presentation.
Thank you, Dr.
Arunprakash, please be in line. We have another speaker.
Okay.
I would like to request Dr. K. Kaniappan sir. Please come online. Jata, please come online and give vote of thanks.
Gratitude is not only the greatest of virtues, but parent of all.
Sorry for the interruption. We have received some questions from the audience. Let me first finish the questions, then go for vote of thanks. Sorry, sorry for this. Sir, I will ask the questions. I will start from Dr. Arunprakash.
Yes, Doctor.
One of the participants have asked, what will happen if the salt bridge is replaced by a conducting metal wire in an electrochemical cell? I will repeat the question.
Okay.
What will happen if the salt bridge is replaced by a conducting metal wire in an electrochemical cell?
Thank you. It's an interesting question and also a very basic question. So the main purpose of the salt bridge is to avoid the buildup of the ions. For example, in your electrolyte solution, it will have cations and anions, and it will be moving freely. So if you have a salt bridge, then you can control the flow of the ions, and also you can minimize the potential buildup. Also, the salt bridge should be very stable, and it should not release any metals into the electrolyte. If you use a metal wire, then you are applying some potential or something, then metal corrosion will also happen, and metal ions will be leached into the electrolyte. In that way, salt bridge is more efficient than a metal wire. So also metals are always prone to oxidation, whether it is exposed to the electrolyte solution or whether it is exposed to the atmosphere due to aerial oxidation. So it is preferred to use salt bridge rather than a metal wire.
The next question is, what about photocatalytic material in nanotechnology?
Okay, it's a general question, but interesting question. So photocatalytic material, so because my talk is mostly focused on the electrocatalysis, so I didn't explain anything about the photoelectrocatalysis. So the photoelectrocatalysis or photoelectrocatalytic materials are also receiving equal attention recently, similar to the photovoltaics. So a lot of materials have been prepared for photoelectrocatalysis. The main reason is people are focusing on the sustainable material development, since solar energy is abundant and you can use solar energy for driving your electrocatalytic reaction. People are trying to develop PEC system, photoelectrocatalysis system. photocatalytic material is the material which can catalyze the reaction in presence of the solar light. It can be UV light or a visible range. So it is preferred to catalyze the photocatalytic activity in the visible region. The materials that can be used as photocatalysts are TiO2, zinc oxide, and several materials are available. And also people are using quantum dots like semiconductor quantum dots like cadmium selenide. The key parameter for a material to act as a photocatalyst is the band gap. So it should have a valence band and a conduction band edge, and the difference between the valence band and conduction band constitute the band gap. For TiO2, it is around 3.2 electron volt. If you can modify the surface of TiO2 and if you can minimize that band gap, then it can perform very well. So people are trying to create some heterojunctions like PN junction by modifying the surface of TiO2 and with zinc oxide or different materials can be prepared. The main purpose is the photocatalyst will drive the reaction in presence of the sunlight, that is called a photocatalyst. The materials of interest are TiO2, zinc oxide, and semiconductor quantum dots. Thank you.
And the next question, sir, as pure hydrogen is very dangerous to use, ammonia can be used as a source of, can ammonia be used as a source of hydrogen? Also, which electrodes are more useful for breaking of ammonia into nitrogen and hydrogen?
Okay, thank you. Interesting question. Because we mostly focus on the water splitting or water electrolysis, splitting water into hydrogen and oxygen. This is another alternate way of producing hydrogen by decomposing ammonia. There are two ways. One is nitrogen reduction. Nitrogen reduction will generate ammonia, like Haber's process. But ammonia decomposition means you have to supply some heat energy. Usually ammonia decomposition occurs at 350 to 450 degrees centigrade. That is a big challenge. You have to set up an electrochemical cell like solid oxide fuel cell or something. And the material or your catalyst should be highly stable at that high temperature. So there are a lot of difficulties in ammonia decomposition. One is the high temperature operation, and the materials used for ammonia decomposition are mostly iron-based catalysts. The best benchmark is ruthenium-based materials. Ruthenium-based catalyst doped with some alkali metal cations like potassium, rubidium, or cesium are used as the catalyst. So iron is the well-known inexpensive catalyst for the ammonia decomposition. But the benchmark catalyst is ruthenium. People are developing other alternate catalysts also, like forming alloys with platinum, nickel, and other metals. The best one is iron. The benchmark is ruthenium. Thank you.
And the next question is, even when we produce hydrogen, what about the storage problems?
What are the storage problems? The main thing is water splitting catalyst are, there are a lot of catalysts like molybdenum sulfate and many catalysts are available, but storage is a very big problem. The main thing is whatever hydrogen we produce should be used in a fuel cell for powering a vehicle or something. So we should have a highly porous or high surface area material. So creating the high surface area material or highly porous material with micro and mesopores can help to store the hydrogen. So the hydrogen storage research is also an interesting topic, and people are trying to use MOF materials, metal organic framework based materials, and zeolites for hydrogen storage. But these materials are a little bit expensive. The cost of producing these materials is a big challenge. Once we prepare some sustainable materials with high surface area and with a lot of pores, then it is possible to store the materials. The material should be lightweight, and also it should be highly porous and high surface area. These are the three important characteristics of a hydrogen storage material. The good examples like carbon aerogels. Carbon aerogels are ultra light materials, and it can be used as a hydrogen storage material even in aircraft or anything. So it is possible to, but there are quite challenges, a lot of challenges which needs to be overcome. Thank you.
And another question, sir, can
Yes.
we use copper catalyst in catalytic converter?
Yes, it is possible. The catalytic copper is the main thing. Is copper is an abundant material, and it is also an inexpensive catalyst. For instance, in the case of the catalytic converters, people use platinum-based materials or platinum, palladium, and ruthenium. These are the noble metals which require high cost for the fabrication, and also scaling up the reaction is very difficult. But when you use copper, which is an abundant metal and also an inexpensive metal, then definitely you can reduce the cost of the catalytic converter. But it is possible. These catalytic converters are mostly used for some minimizing the pollution or removing the pollutant. Care should be taken. Copper should not be leached from the electrode surface. Otherwise, copper contamination will also happen. But definitely, it is a good solution to use copper because it is very inexpensive. Thank you.
Yes, sir. I think some connectivity problem at Dr. Suresh in.
Okay.
Participants have asked some questions.
Okay.
So, may I put it forward to you, sir?
Yes, sir. Definitely.
Since you have already worked on sensor.
Yes. Yes, please.
For the benefit of participants, let me ask questions.
Sure.
Can you explain micro and nano array electrode-based sensors? What are the advantages? What are their advantages?
Okay.
Micro and nano array electrode.
Okay.
Based
So, okay. The array electrodes means an arrangement of the electrodes. Instead of having a one electrode, and you will have n number of electrodes arranged in series. It can be of nano size or micro size. If it is of nano size, it's called nano array electrodes. You can construct the nano rods on a substrate like silica, and you can create nano array electrodes. Similarly, you can also create micro array electrodes. The electrodes will be in the micron size. These electrodes allow you to direct multiple analytes. For instance, if you have a screen printed carbon electrode, it is a single electrode. It will have only one specific working area, and you can detect only one analyte. If you have a nano or micro array electrode, you can detect multiple analytes. For instance, if you want to detect glucose, hydrogen peroxide, or other analytes, then you can use the micro or nano array electrodes. The main advantage, you can detect multiple analyte. The other one is sensitivity will be much higher than the normal planar electrodes. The micro and nano array electrodes have high sensitivity and selectivity, and also multiple analyte targeting is possible. So these are the advantage of nano and micro array electrodes. Thank you.
Yes, sir. We have some more questions for Dr. Suresh. Actually,
Yes.
he is not online.
Okay,
There is some connectivity issues. So, participant, I will post his email address here so that you can send your queries directly to him. He will clarify you through email. Now, let me ask Dr. M. Sujata to give vote of thanks.
Gratitude is not only the greatest of virtues, but parent of all others. Thank you is the priceless gift. A very pleasant good evening to one and all present here. On behalf of Chemistry Department, Chickenna Government Arts College, Tirupur, it's my great honor and privilege to propose a vote of thanks on this memorable occasion, a resounding success. First and foremost, I thank our special young chief guest, Dr. Arunprakash Periyasamy from UK, on his beautiful lecture on electrocatalysis. You envisaged us with energy-efficient catalyst and its significances for our current need and future goals in electrochemical field. Thank you so much, sir. I am grateful to thank our another young chief guest, Dr. C. Suresh from Sikri Karaikudi, for his efficient lecture on nanosensors. You enlightened us with much information and applications on nanosensors in healthcare, food analysis, environmental and security, and also in COVID testing purposes, especially in pesticides and food contaminations, etc. You both made this international webinar a meaningful and grateful one. Thank you so much, sir. I take this opportunity to express our sincere thanks to our dynamic and honorable principal, Dr. C.V. Deepa ma'am, a well-wisher in all our activities, for her vision and untired support in gracing this occasion. Thank you, ma'am. I'm grateful to beloved HOD Dr. G. Rajagopal sir for his eminent guidance and motivation in all our endeavors. I thank him for his constant support, kindness, and hospitality to all of us. Thank you, sir. My special gratitude to our organizers, Dr. P. Vijayan and Dr. K. Kaniyappan sir, for their dedications in smooth conduct of all the virtual webinars, a memorable success. Special thanks to you both, sir. Finally, I would like to take this opportunity to place on record to thank our team members and colleagues of our chemistry department and all the distinguished invitees from all over the countries. Thank you all for your kind attention and cooperation. Thank you one and all. Have a nice day.
Thank you, ma'am. Thank you for one and all present here. It was a great pleasure to us. Thanks for your cooperation and participation. Thank you for the speakers. Thank you, sir. Thank you very much. I'm going to end up the session, sir. Thank you.
Thank you.